Everybody's taking notes. Let's generate this recursive sequence where you're given t sub 3, t sub 1 equals 3, that's the initial condition, and t sub n equals 2 t sub n minus 1 plus 1, that's the recursion equation. To define some recursively, you need two parts to it, okay? We're not doing this on the calculator just yet, Joe. We will. So t sub 2 equals twice t sub 2 minus 1 plus 2, or t sub 2 equals twice t sub 1 plus 2. See how you're defining a term in terms of the previous term. Yeah, I'm sorry, I wrote down the recursion equation wrong. That should be a 1 there. Plus 1. So that's twice t sub 1, which is 3 plus 1, and you get 7. So guide me through finding t sub 3 now. Right? Plus 1. So twice the previous answer, 7, plus 1, and we get 15. Now you can also do this on your calculator very quickly and generate the whole sequence. Let's try that. On the T99, you can just hit 3 and hit enter. I hope I didn't put this up here already. No, I didn't. 3 and then hit enter. Now it might seem silly to you that, why would I hit enter? I haven't done anything. Well, you want it in the display of the calculator so that now you can do the recursion. So this is the first step, initiating the sequence. And now the second step is going to be 2 times answer 1 plus 1. And then hit enter. Yeah, the answer is above the subtraction gate on the bottom there. And then you can just keep hitting enter. So give me the first 10 terms here. Well, let's start with 3, 7,
15, 31, 63,
10, 27?
127.
127.
255. 511. Okay, this is 1023. Oh, it does work. How much do you want more?
No, that's 10, right? Thanks. Yes, it does work. Let me see what you're doing. Put in 3 enters. Now, 2 times the answer from 4. Oh, you got 65. Yes, you have to be given both parts of a recursion in order to generate a sequence. Yes, questions? Not working? You're not putting any in? 2 times the answer. You actually have to put that in there. Love these subtractions.
Yo, Robbie.
Right. Yeah. Now, this is what's nice about the 89 is you can do more than one previous answer. That's why it's answer sub 1. It's the first answer going backwards from your current window. So you can do answer 2, answer 3, and so forth. Okay, let's look at this sequence. Write the recursive formula and also an explicit formula. So the recursive formula has to come in 2 parts. Right? What's t sub 1? And then t sub n will equal the previous term minus 3. If they actually look at the whole value, okay? T sub n minus 1 minus 3. Explicitly, we'd use t sub 1 again, right? But now we use the common difference idea of 20 minus 23 is negative 3. So t sub n equals t sub 1 plus n minus 1 times d. So you get 23 plus n minus 1 times negative 3. And maybe we expand that out, 23 plus negative 3n plus 3. Or we get t sub n equals 26 minus 3n. Notice you need 2 parts for a recursive formula. You only need to have the one equation for an explicit formula. which is the better? Why is the first one better? It's easier for generating the first few terms. So it kind of depends on what you're being asked. If I was just asked to quickly generate a few terms, I could just keep, I'm going to start with 23 and keep subtracting 3. But now if I'm asked for the 100th term, now the recursion becomes tedious. And the explicit formula gets in there right away. Oh, the 100th term is 26 minus 300. Right? You're there right away. So that's the advantage of the explicit formula, getting you quickly to anywhere in the sequence you want. The recursive formula is handy for generating the first few terms of the sequence. Now sometimes we're just going to be stuck. We might not be able to do it explicitly, or even recursively. Y equals sine x. How do you do that recursively? That's the explicit formula. What if my the function was y equals the sine of x degrees or something like that? Is there a way to take the previous answer and multiply? Well, the sign keeps going up and down, so it's not going to be geometric. It's not going to be arithmetic.
So there's no sequence formula?
Is there a recursive formula for it? Think about it. Okay. Maybe do your degree on it. Yes. Yep.
Wait, but you said if you're trying to find 100 more, why can't you put it in the first one? T of that would be 100.
Right, but T sub 100 then would be T sub 99 minus 3. You'd have to get to the 99th term.
What are we doing with that -3 in the recursive form?
That means subtract 3. Take the previous term and subtract 3 from it.
Oh, okay.
That's what's going on up here, right?
So if you set, like, find T sub 10, or T sub, like, a high number, you would use the explicit formula?
Yes, that'd be easier. Find the first 5 terms of this sequence and find explicit form for T sub n in terms of n. So let's find the first 5 terms. Might as well do it explicitly. Here's the formula. We've got the first term, so the second term is 1/2 times the first term. 1/2 64 is 32. So the third term is 1/2 times the second term, and you get 1/2 of 32, and we cut it in half down to 16. And I think you see we just keep cutting it in half. So 64, 32, 16, and 4. There's our first 5 terms, right? And find the explicit form for T sub n in terms of n. Do you notice what kind of sequence it is? It's geometric. Geometric. And you can tell from the recursive formula. If you strictly multiply the previous term by a constant, then that's the whole idea of a geometric sequence. So the common ratio is a half. In fact, remember that's one of the ways we define the common ratio is the ratio of 2 successive terms. And from this formula directly, you can get T sub n over T sub n minus 1 equals 1/2. There's our common ratio of a half.
So it would be T to the n equals 64.
T to the n?
Or I'm sorry, T sub n.
T sub n.
Equals 64 times quantity, R, and then n to the power of n minus 1.
There you go. So T sub n is 64 times a half to the n minus 1, which is 32 to the n minus 1.
No.
No, okay, so people are really quick on that today.
Isn't it 32?
You could stop there. What if you want to fix it?
Is it 32 times 1/2 and over 1/2?
1/2 to the n over 1/2 to the first.
Oh,
So you could write it as 128 1/2 to the n. So I accept that too. Okay. But this is fine with geometrics.
No.
Yeah.
Well, 1/2 to the first.
Yeah, why is that 32?
It's 1/2 to the n over 1/2 to the first. And doubt me no more.
Divide by half is multiplied by 2.
This is true. Now, notice here, with this formula we first started with, is this arithmetic or geometric? Arithmetic? We'll look at the sequence. We went from 3 to 7 to 15. Up 4, up 8. Nope. So it's not arithmetic. It's not geometric. Does it end up being quadratic? let's look at these. Let's look at the ratios here. You go up 4, up 8, up 16, up 32.
Oh, it's
Hold it, no, that's
church.
up 4, that's up 12, that's up 16, which is up 8, and then that's up 4. What? Oh, see, it's not necessarily following
So there's no.
a polynomial expression.
Well, is that because you're both multiplying and adding in the original equation?
Yeah.
So it's nothing.
Yeah, see, so that brings to mind, take a quadratic sequence sometimes, and see if you can write a recursive formula for that. Okay, it's good extra credit project. Extra credit project, okay? Now you got me, right? Okay, here we go. Population of a certain country grows as a result of two conditions. The annual population growth is 1% of those already in the country. That is the growth rate minus the birth rate minus the death rate. People die. People are born. Thank you, Michelle. Okay.
How does that work?
But you have such a happy country, people want to come visit you and stay. Okay? 20,000 people immigrate to the country each year. So, if the population is now 5 million, what will the population be in 20 years? So first, let's do a recursive definition because we're not really given a formula on this, are we? So, the population of N is the growth rate applied plus the immigrants. The growth rate applied, well, it's a 1% growth rate. So you take your previous amount and add on 1% of what you had. That's the growth rate applied. Right? Plus 20,000 immigrants. Just plain old 20,000.
No.
Not times N.
No, it's just 20,000.
Well, no, and because years. It's every year.
No, see, actually we should say piece of N minus 1. Right?
Why?
Because to find the population any year N, you have to look at last year's population and multiply that by 1% and add that on. Now there's a simple way to do this, and that's to say 1.01 times the previous year's population. Plus 20,000.
That's what I did.
There you go. So there's two things going on in this recursion. You're multiplying by a small amount, but then you're adding the 20,000 on. Now what do you think is contributing more? What's 1% of 5 million? 50,000. So actually you're getting more. And actually you're going to build on that after years. So even just in the first year you have 50,000 in net growth plus the 20,000. So, how can we get this on the calculator? There's the recursive formula.
Why is it not?
And remember, hold it, is that whole recursive formula?
No, don't you need 20,000 N's?
No, not 20,000 N. Why are you doing N?
You're just adding
It's every year.
But no, we're just going from the previous year to the next year. 1 year.
Oh, okay.
20,000 people. Now again, do you think you can come up with an explicit formula for this? Look into it, okay?
So you have to put it in 20 times.
20 times, right. That's what we're doing here. So try this in 55 million, first hit enter, then answer 1 times. Now here's the trick too. You can actually just hit times. After you hit enter, 5 million enter, now just hit times, and times is a binary operation. The calculator goes, oh, you must mean you want to multiply by whatever I had on the screen last. And so it'll just put that answer on there for you. Saves a little time, right?
Wait, why do you divide it by?
I did dividing. Answer 1 times 1.01 plus 20,000 and enter. Hit it 19 more times, see if you match by 6,541,330. Okay, you get there? It's a match. Did I count right? Because this is actually actually no, it says in 20 years. So actually after you hit this enter 1, that's the first, that's at 20 years, 19 more times to get it after 20 years. So you gotta be careful with that. Because 5 million, next to that. Sean?
Under my head.
Now, the spreadsheet approach. Have you worked with a spreadsheet approach before?
In Excel? Like
In Excel? course Excel. Is there anything else? Never done spreadsheets before. Oh, that's just sad. I want you to see this. So here's our population. Here's our year. Let's start at year 0. Shh, watch how I do this now. How do I get this so I get all my years from 0 up to 20? You want me to just kind of go 1, 2, 3. I aired already. Right, what should we do here? Equals this cell plus 1.
And then you can copy that cell and then paste
And then control this D down. Boom.
Whoa.
Isn't that nice?
How did you copy the previous cell? Like control and then you clicked it? Did you hit control and then click the cell you wanted to copy?
Control D.
Control D. Okay.
Yes, I always make sure, if you're going to do a control D, it'll copy down. So make sure you have included that at the first cell, okay? So let's try it now here. Let's have someone volunteer to come on up here. I'll get you started. The population at 0 was 5 million, right? And let's just change this so that we get a decent format in here. Numbers. There, we got lots of people now. Give me some ideas. Yes.
Okay, so what you're going to do is you can say equals.
Yeah, got to start a formula with equals.
It's kind of the reverse.
If you don't, it will just evaluate whatever expression you have and put the expression there. Whereas you want a rule in here, a recursive idea in here.
Alright, and then you'll click on the cell above it.
Above it, okay.
And then you'll say times, or the little star symbol.
Times.
And then 1.01.
1.01.
Plus, is it 20,000?
20,000 immigrants.
And then we can do like 20,000.
Enter. Yeah, now, you don't want to control down from here. This doesn't have a formula in it.
No, you want to control down from cell B3.
Wait, are you recording this or is this a video?
Yeah.
Is it voice or picture?
Control D. Okay? And is that consistent with what we came up with? 600? Okay, now, notice what happened here. We made this formula. It doesn't show up here, it shows up here. See that? I'm showing this to everybody because when you sign up for homework problems, this is definitely something you want to present. And you can cut and paste that, or I've got Excel on here, whatever. But notice when I come down here, it's not the same formula. It does relative referencing. It said, when you guys made the formula, you referred to the cell above it. So even though it says B2, in its memory, it's thinking the cell above the current cell. That's why when it copies down the formula for B4 will involve cell B3.
So can you extend those again? Could you extend those again?
Yeah.
Distance from the cell.
Yeah. Okay. All right. Great. We'll copy that in there. Let's get back to it then. Good job. You did much better than their class. They haven't tried it yet. So let's be fair.
There are like 8
What are we go up to here? Year 20. Oh gosh, that's not going to be good. Let's see what happened. Oh, it's fine. It's fine. What the? There you go. Good job, gang. Good job. Not sure. Okay, now the Fibonacci sequence. Sure you've seen this before? Now we're going to formally do it in terms of recursion. Sometimes recursion can refer to 2 or more previous terms. So you've got T sub 3 then is T sub 2 plus T sub 1. That's what we mean by T sub n minus 1 plus T sub n minus 2. So the third term is 1 and 1, or 2. fourth term then? T sub 3 plus T sub 2. So T sub 3 is 2, T sub 2 is 1. You get 3. Then T sub 5 will equal T sub 4 plus T sub 3. 3 and 2 is 5.
What's that pyramid called?
So it's 1, 1, 2, 3, 5. And then add up these two. Ching, ching to make 8.
They got 11.
Right? And then add up these two. Ching, ching to make 13. And then you add 21 and so forth. Okay? Alright. That's the Fibonacci. Let's try it on your calculators now. Try it on your calculators. It's a little trickier because you have to go 1 enter, and then answer 1 plus answer 2.
How did you answer 2? You just go
Edit.
click answer, and then you go in and you delete the 2, 1, and add in a 2.
There's 2 answers. One of my favorite Fibonacci numbers is also has an English term for it.
Oh, yeah.
Like British?
This is a name for a number bigger than 100. You should know this number. Jumbo, no. Bigger than 100, less than 200. It's a term you should know.
2, 3, 4.
It's called a dozen dozen. A dozen dozens.
That's not 5 letters.
It's a hint. It's a hint. A dozen dozen has a special term. You're going to get into shipping, packaging.
Gross. It's gross.
Gross. There you go. Gross. Okay, find the gross thing in here. Go for it. Find the gross number. I believe it's in the Fibonacci sequence. It is. Find it between what and what?
Nobody say it.
Wait, how can there be ever
13, right? 21, 30, 4, 55, 89, 144. There's that
I'm
gross.
already in 46,000.
It's 12 squared. Now, I want to do this on the spreadsheet. Now that you're all fully trained, I'm randomly going to pick a volunteer. One, right? Actually, let's call this Fibbo. There, I got you set up. Now, I'll even put the equal sign down for you. Come on. Thank you. Thank you. Where's the curves in your generation?
A2 times A3.
Wait, it was addition, right? Yeah. Okay, then. All right. Good try, Joey. But
Oh, Joe, it's not multiply.
I don't know how your mouse works.
You can do it.
Wait,
Yeah, you can do it. You can do it.
Just hold on.
Grab it. Yeah, control. You gotta, click and drag. Yeah, oh, yeah. Far enough. No, no. Oh, yeah, there you go. Control D.
Yeah.
There's the gross right there. Okay. Now, is it arithmetic?
That's how you spell it.
Arithmetic. Is it arithmetic? What do we have to do for an arithmetic sequence? Subtract successive terms. Make sure you go in the right direction. Don't underscore them. No, we did not get a common difference.
Let's keep going. Let's like do it again.
So, is it geometric? It is indeed geometric, apparently.
That's how it is.
Because it has been declared. It is so. This divided by this.
It's definitely not like a.
It's not. It's not a real sequence. It can't be.
Why? I think it's a sequence just in the.
But,
It's close.
but, ratios approach something. They don't just go down to 0, right? Further, Fibbo starts with 1 and 1, but the flangio sequence starts with 12 and 20. Because that's where he used to live at 1220. And the ratios still end up approaching the same thing. You can put any numbers you want into there, and you still end up with this ratio. So it's such a key ratio, let's give it a name. And it's important to some. So we call it a word, and we call it
Robbie.
I think that's the name of it, aum. Let's find out.
For action.
There actually is an explicit formula for the Fibonacci sequence. Would you like to see it?
Yes.
Here she is, the Princess Buttercup.
Yes, Princess Bride.
Look at that. Wow. Huh? And this 1 plus the square root of 5 over 2 is what we saw in that ratio before, right? Also known as the Lagina man. No. Shuffle that. Shuffle. Wingnut, no, not Wingnut Doozer. Along with Flange and their daughter Cockerpin. You probably are not ready for the
Wait, what's your daughter's name?
the Doozer movie. Lagina man, come on, rearrange it.
Golden name.
Golden.
Number.
Golden
I
drum.
thought it
1, 8,
was
6, 1.
I thought it was the golden ratio.
Golden egg.
Golden.
Golden egg.
Use these
Golden
letters.
mean.
Golden mean. There you go.
Golden right.
Golden mean. They actually use the letter phi for it sometimes. And it's that ratio to golden right. Shows up in the Fibonacci sequence. And further, are you getting that effect too? I'm getting that effect. Definitely getting that effect. Well, what you can do is print this up, and it's like a sunflower thing, and just choose how you want your radii. So you can either kind of go along like this. I could say, I'm going to have this be my curl, and keep continuing that pattern, complementing each direction. Or you could say, oh no, I'm going to go this way, like this. So it's a fun activity. Count the spirals in each direction, and I think you'll find it very amazing.
They're all the same?
No. Careful what you focus on. All right. At this point, you got 10 minutes. You can get 10 minutes homework done. I'm going to come around. The other class doesn't have a chance to sign up yet, so you can't sign up for your second. And in fact, you only sign up for your second if you've got the first one done.
Can I see what my problem was?
Yes, I will call that up again. I'll bring that up shortly. Start working on 2.
Check the review.
Don't you stop recording?
Yeah, pick up from there.
Oh, good point. I'm going to stop recording now.
No.